Okay, hello everybody. Clint here from WE214. This will be my first recorded lecture, and what I'm going to do is try to present lectures in this format in kind of the same way I would have presented them in class, except for, of course, it's recorded and nobody can see me. But the flow should be about the same, and I'll try to keep about the same content as well. Every day or so I'll post a new lecture until we get through the remainder of the material, and I'm hopeful that that will give you all the information you need to go and complete the labs. So this first lecture is going to be kind of a short one. I want to pick up a topic that I don't think I developed fully enough earlier, and that is XOR functions and looping XOR functions out of K-maps. So we defined early on the XOR function to be like an OR, except in the final row where A and B are both 1, the output's a 0. And we define an XOR gate, looks like that, to be the XOR function. And then we went on to look at a 3-input XOR function and motivated that for a 3-input XOR, or really for any number of inputs, that you can think of the XOR function as an odd detector. In other words, the output of the XOR function of any number of inputs will be 1 whenever there's an odd number of inputs that are asserted. So in this row, and this row, and this row, and this row, we have an odd number of inputs asserted, so the output would be 1 in those cases, and then 0 everywhere else. So that would be the XOR function in 3 inputs. Now if I look at the XOR function here in a K-map, let me just do that real quick. A, B. I'm going to get, just transferring information from the Y column into the K-map, I'm going to get a 1 in the cells where there's an odd number of inputs asserted and 0 elsewhere. Now, we've always said you can't really loop diagonals, and that's still sort of the case, but in a K-map, when you see a diagonal pattern like that, that's indicative of an XOR relationship. And the way you might think about this is you might notice for this one here where A is a 1, B is a 0, and for this one here where A is a 0, B is a 1, and that kind of defines, well, that does define the XOR relationship between A and B. If I looked at the K-map for this 3-input XOR, it would look like this. I'm going to put a 1 in every K-map cell where there's an odd number of inputs, just following, or just transfer it directly from the rows and addresses here. So I'm going to get a 0, 1, 0, 1, 1, 0, 1, 0. And again, you'll notice kind of a diagonal pattern where I've got these ones offset from each other. Now, if I just saw this K-map by itself and we were going to loop it according to the rules we've developed so far, I'd have no choice but to loop everything individually and write down 4 terms, with each term being a min term, containing all the input variables. And I could certainly do that. That would be A, B bar, C bar, or A bar, B bar, C, or A, B, C, or A bar, B, C bar. That's not particularly simple looking. I could also observe that in the B bar part of the map here, so here, that's the B bar part of the map, because B is a 0 in those rows. In the B bar part of the map, I could observe this diagonal pattern again, where A is a 1, C is a 0, and here for this one, where A is a 0, C is a 1. So in the B bar part of the map, I've got the A, X, or C relationship. And then I could notice in the B part of the map, where B is a 1 for this half of the map. Then this one shows up where A is a 1 and C is a 1. And this one shows up where A is a 0 and C is a 0. And that's the XNOR relationship. A XNOR C. And that's in the B part of the map. So that's maybe a little simpler than this equation. And of course, the two are logically equivalent. But I could make one more observation as well. The XOR relationship occurs whenever I've got two quantities, call them alpha and beta. If I've got alpha and beta, or alpha and beta, and I'm using alpha and beta because alpha might be a single variable, or it might be a collection of variables like an OR or an AND or an XOR relationship. When I have this relationship and I've got alpha inverted in one term and not in the other, and the opposite for beta, not inverted in one term but inverted in the other, that defines the XOR relationship. So that's just the XOR relationship between alpha and beta. And I've got that going on here, where now my B variable is taking the place of alpha up here, and the quantity A XOR C is taking the place of beta. So this whole relationship then could be written as B XOR alpha, or A, sorry, XOR C. Right? And then we talked about distribution and commutation earlier. I could rewrite that in a more simple form of A XOR B XOR C. So this K-map here results in that simpler equation A XOR B XOR C. All right. The XOR relationship can also show up in other forms other than just these diagonal patterns. For example, let me get a new page here. I might have a K-map that looks like this. When I have those sort of offset patterns, not diagonal in this case, but offset, that also can indicate there's an XOR relationship hiding there. In this case, it's a bit more obvious. If I looped those two terms and those two terms, I could immediately write down that this is B bar and C, or C and B bar, and you'd, I don't know what I did there, I'll do that again, sorry. B bar and C, or B and C bar, and you could recognize right away that that also is an XOR. There's a couple of other patterns that are characteristic of XOR relationships in K-maps, but I'm not going to go any further with that right now. I wanted to point this out here, though, because when we get into the next section and I talk about circuits that can do arithmetic operations, it'll turn out that there's XOR patterns hidden in those K-maps pretty frequently. Okay, that's it for this lecture. Join me for the next one.